this submodule, I will introduce you to the basics of application writing, starting with classical communication, how to create EPR pairs, and how to do local qubit operations. We will lastly explain the function of the program meta object. A user has to write the code that they wish to perform in a program inside the run method of a program class. This run method is given a program context. This program context contains the various objects that you need for your quantum program. These are, for example, the connection object. The connection object represents the connection to the QMPU, and we use it to send the instructions that you compile to the QMPU and make the QMPU execute these instructions. Then we have classical sockets. We obtain the correct classical sockets for, in this case, to Bob by taking the context.csockets. And then this csockets object, this is a dictionary, so we must address it with the correct key to get the correct socket we wish to get. In this case, we want to have the socket to Bob. But in order to avoid typos and make the code more reusable, we will be using this self.peername, this class variable, in order to make this a little bit easier for us. Then lastly, you can get the EPR socket from the context. So this is similar to the classical socket. We need to pick out the correct EPR socket, in this case to Bob. Then in order to do classical communication, we simply need to use the classical socket. So we take the csocket and then use the send method. And then we can put whatever message we wish to send. So for example, we can put hello from Alice over here. Now we can copy this code up to the Bob program. And then we can finish the required code in order to send this classical message. So Bob needs to receive instead of send. He will get a message. And then we will print this message. Now, in order to make this code work, we need to add this yield from statement over here. This is because we need to wait for the event that the classical message arrives at Bob's side. And this is, again, due to more deeper technical reasons of how the SquidAsm integrates with the event engine underneath. But this is, for a user, this practically always boils down to that they need to add these yield from statements in 3 locations where they are waiting for a program for something, namely when they are waiting for classical messages to arrive, when they are waiting for the QMPU to finish completing its instructions, or when they have created a method that has these classical messages or QMPU instructions inside, and they wish to invoke that method. So now we can run this code by pressing Shift F10, and then we can see we have our message arriving. Bob has received a message from Alice. Now let us move on to generating entangled qubits via the EPR socket. So the EPR socket, it functions a little bit similar to the classical socket. We take the EPR socket, then we use the createKeep method. From the createKeep method, we will get a qubit object. And we have to select the first element out of this createKeep. That's because this createKeep method is set up to generate a list of qubits where you can specify the amount of qubits via the number argument. Per default, this number is set to 1, so we get a list of 1 qubit out of here, and we have to select that 1 qubit out. After receiving that qubit, we can directly measure the qubits and store the measurement result in the variable m. Next up, it's important to note that now we have to send these instructions to the QMPU. And in order to do that, we use the connection object and the flush method. This will both compile and send the instructions to the QMPU. And then we wait for the QMPU to finish these instructions. Lastly, we then print the value. So Alice measures. Then we take this piece of code and copy and paste it to Bob's site. So Bob has to use a different method. He needs to use the receive keep. That's because while the entanglement generation process is symmetrical, the sort of preceding software interaction, it has an initiating party and a receiving party. And we distinguish those by using either the create keep or the receive keep methods. And then with that, we can run this code. And we see Alice and Bob both measure 1. So this 1 means that measurement in the Z basis was performed and they measured up. If we can run it a few more times, we see that we get either 1 or 0, but they're always they're always the same. That's because the qubits, they're perfectly entangled. Because of the underlying model that we've used is to generate perfectly entangled qubits between Alice and Bob. Now, next up, we might want to generate local qubits in order to do some operations where we don't have a qubit that's entangled with another node. For that, we need to use the qubit object, and then we give that a connection. For this example, I'll be using 2 qubits, and I'll apply some gates to the qubits. So the qubit objects, they have various gates you can apply to them. So all the single qubit gates, you can find them like the X, Y, Z. You can also have the various rotation gates over here. And you just simply apply a gate by placing the method of the gate that you want to apply to the qubit. So currently we have a circuit where we only apply a Hadamard gate to the first qubit. 2 qubit gates work a little bit differently, but also still quite similar. There's only two qubit gates. We have the controlled phase gate, and we have the controlled CNOT gate, which we'll be using. The 2 qubit gates work by the first qubit you use, that's going to be the control qubit, and the second qubit that you provide as an argument, that will be the target qubit. So we now have a small circuit where we first rotate the first qubit and then apply a CNOT, and that will entangle both of these qubits with each other. And then after that, we will perform measurements of both qubits. Then we need to send these instructions to the QMPU. And again, we do that by connection.flush. And then after this, we can print our results. And we now run our code with Shift F10. We see that we get the same result for M1 and M2. If we run it a few more times, we see they all find like 1 or 0, but they're always the same. Now, lastly, we have to discuss briefly this program meta object. This program meta object, this specifies the requirements of the program on the network. So in this case, what we're saying in this line is that in order for this program to function, we need to have a classical socket, a classical connection to Bob in this case, and also that we require an EPR socket to Bob. If we do not specify this C socket, then we will also not receive this C-socket. So for example, if I now try to run my simulation, I encounter an error that will happen on this line. That's because this C-socket object is not available inside this dictionary over here.